formation. In fact, with some people at the Mathematical Research Institute, we currently prepare a new application for so-called Dachstuhl seminar, which is a one-week seminar between computer science, and sometimes they allow economists there as well. And the idea is that you have a 1 week, it's somewhat in the middle of nowhere, so you have lots of time to listen to talks and actually also sit around in working groups. And the question is, how do you form working groups? So, so how to partition the participants into the working groups, also based on the preferences of those participants. And that's basically a so-called hedonic coalition formation problem, and I'm going to talk about that. And our focus is on good outcomes. Well, what are good outcomes? In our case, we are thinking about core stability. So an outcome is this partition. And we are thinking about a new type of situation, aka preference domains, where we have existence of these good outcomes. And on top of that, and that's the cherry on the cake, we are going to have implementability in terms of truth telling in weakly dominant strategies, aka strategy-proofness. So the model is very simple. So we have n agents, like you are sitting here in this room, and a non-empty subset is called a coalition. And what we are going to have is that people have preferences over the coalitions they can be members of. You don't care what the other people do, you just care about your own group. And the preferences of the preference domain is denoted by RI. And what we are interested in are preference profiles. So I want your input of who you want to be with in order to determine what partitions we are going to look at. Now, a hedonic game, or for short, a problem, is a set of agents and their preferences over the coalitions they can be members of. So it's a very simple model. And an outcome for a problem is a partition into coalitions. And then you consume your coalition in a working group, for instance. Now, we denote partitions by pi. And the preferences I'm going to talk about are assuming that you are able to consider how you think about another person together with yourself. One assumption I make right now, but I will drop it at the end of the talk, is that you're not indifferent between being alone and being with somebody. Again, I'm going to drop it, but for now, we are assuming this. Now, the moment I make this assumption, I can actually partition the set of agents into two types of groups, namely the friends. So the friends are the ones where I'm preferring being with this person. So maybe, Attila, I would prefer to be with him than sitting alone and think about stuff. So then Attila is a friend. And vice versa, if I prefer to be alone instead of being with somebody, then that person is an enemy. Of course, this is a bit strong, right? I'm not really thinking about enemies and friends, but think about it. You'd rather want to work with somebody. It's a productive person in your working group. Or, for instance, maybe somebody is very quiet. They just sit there. I still would rather not have them there because maybe they end up on the publication and then I'd rather not have that co-author who didn't do anything. So we are going to divide the set of people into, you are going to divide people into friends and enemies, and we are sometimes just denoting them a little bit more simply without putting the preferences as inputs. Okay, now we are not assuming that this is symmetric. I might think, Attila is my best friend, but actually he'd rather not see me. So no reason for this to be symmetric. Now, the point is that we will use this to define a fairly big domain of preferences called friend-oriented. So preferences are friend-oriented if adding only an enemy is bad. There's somebody in my group and who comes in, I don't like them. The group just became worse. My coalition just became worse. And of course, I also will assume that adding a friend is good, but here we are doing a bit more. It's a bit like putting more emphasis on the friends. You're talking about research in the working group. Some brilliant, creative guy, for me, is much more important than these people who sit around and don't do much. So basically, we are applying some lexicographic tie-breaking here in the favor of friends. I'm also going to mention what happens if you do it the other way around, if you put the emphasis on avoiding enemies. Of course, this could happen as well. It changes the result. It is important. So this means that when I'm adding a friend, possibly with a set of enemies, it's still a better set. Okay, so we are going to denote the domain of friend-oriented preferences by script F. And here's just a little bit of an example that shows you what happens. So the notation means one, we look at a preference of agent one. He has two friends and a bunch of enemies. The best coalition for agent one is when he is there and his best friends. So the best is always when you're together with just your friends, nobody else. And then we can see that when you add an enemy, the set gets worse. And here we add even more enemies, the set goes down. And here we're removing a friend. Again, that's super important. The friends are important. So again, the set gets worse. So this is a better set. It has another friend there. And now we add an enemy again, and so on. Now, at some point, you're alone. And down here, you have all sets that have only enemies. Okay. Now, there are subdomains of these friend-oriented preferences that we can easily illustrate. One was introduced by Dimitrov, Bohm, Hendricks, and Sung. They called it appreciation of friends in the coalition formation context. And basically, what you do is you just count. Now, you have two sets, two coalitions you could be a member of. You count the number of friends. The one that has more friends is the better coalition. If you have equal number of friends, you just count the enemies, and the one with fewer enemies is now the better coalition. So you just count. You have lots of indifferences. Now, we also introduce a so-called lexicographic preference domain where you have a ranking of everybody. So I rank you guys, and I put my somewhere. So some of you are friends, some of you are enemies. And in any coalition, I just look at my best friend, the best person in that coalition. The set with the best person is the better coalition for me. Now, if the best friend is the same, I go to the second best, and so on. So this is a lexicographic extension of a linear order over coalitions. Now, this is, of course, only having strict preferences. This is a strict preference relation. Now, here's a simple example that illustrates to you quickly that this is a big preference domain. We have 4 agents. Agent 1 has friends 2 and 3, and enemy 4. And we're looking at the preferences of agent 1. Now, there are 13 distinct preference relations that are friend-oriented. 7 of them are strict. The other ones have some indifferences in them. One is the appreciation of friend preference relation. And of course, since this guy has 2 friends, 2 can be the best friend or 3 can be the best friend. You have 2 lexicographic friend-oriented preference relations. So I'm just showing them to you here, the weak ones. These have some indifferences somewhere. Here you have the 2 lexicographic ones, 1 and 2. And here you have other strict friend-oriented preferences. So that's just for this simple example. You already see you have lots of friend-oriented preferences. Now, in this research on hedonic coalition formation, there already has been a preference domain that was suggested as very nice because it guarantees the existence of core partitions, of core solutions. And that was the so-called top responsiveness domain by Alcalde and Revilla. Now, top responsive, I don't want to spend a lot of time with this, but their work on choice functions, so you give me a bunch of agents, I'm able to say this subset is my best set. So part of this preference domain is that each set of agents, you can select the best set for you from that. It's a unique maximal element of that choice function. We just saw choice functions. And then it happens to be the case that first you have to have that when the chosen set from S is better than the chosen set from S prime, then S is better than S prime. This is not satisfied by all friend-oriented preferences, by the way. And the second one is, well, if the choice from S is equal than the choice from S prime, then the smaller set is better. This we have because when you choose from a set, the best set from a set is only your friends. If 2 sets have the same friends, then the set with fewer enemies wins. And that's basically the second condition. First one is not satisfied. Now, what I want to illustrate with this is that what we do is quite independent of that domain. Here you have the Venn diagram that illustrates the top responsiveness domain. The appreciation of friends domain is in the intersection with top responsiveness and friend-orientedness. Friend-oriented lexicographic preferences are completely separated from top responsiveness. And we talk about domains that live in here. There can be everything, there can be parts of this. Okay, so here you have an example with 3 agents. Agent 1 likes agent 2, I'm just going to have a quick diagram here that I will also use, and agent 1 likes agent 2, agent 3 likes agent 2, and actually agent 2 likes both of these agents. I'm not going to denote that at the moment. And that implies unique preferences for each of these agents according to friend-oriented preferences. I just have 3 agents. And right now, it's just important that I have 5 partitions. Everybody's alone, everybody's together, or one person is alone. Okay. So we are interested in good solutions. So I'm going to introduce core allocations to you. It's a very classic concept. In general equilibrium, we talk about cores, and core allocations are defined by a blocking notion. Usually in economics, it's you take your endowment, you reallocate it, and you get a better allocation. That's the blocking. Here, what you do is you split off in a different coalition, because you're your own endowment. You can take yourself somewhere else. So a partition is weakly blocked by a coalition if everybody in the coalition is at least weakly better off and somebody is strictly better off. Weak blocking determines the strict core, because the strict core are all the partitions that are not weakly blocked by any coalition. And we define this, we just the strict core by SC. Now, there is weak blocking here. If we, sorry, there's another slide in between. Clearly, there are 2 specific blocking notions. You block with yourself. If that's not possible, you have an individually rational partition. And you have Pareto optimality, when the grand coalition cannot weakly block. Now, the other blocking notion is that of strict blocking, or just blocking. So that happens when the coalition, everybody in the coalition is strictly better off. And the absence of blocking coalitions defines the core. And by definition, we can very easily see that the strict core is always a subset of the core. That's just by definition. It's more difficult to block this way than in the strict core. Okay. So one observation we can make quickly is that the strict core can be a strict subset of the core. So here we have this sort of example where agent 1 likes agent 2, agent 3 likes agent 2, and the point is that agent 2 likes both of these guys equally. So he points here and he points here, but they are equal friends. That leads to preferences that look like this, because this is the same to agent 2, and that's okay. And now what we can see is that there's a strict core allocation, namely the grand coalition, because everybody likes agent 2, so he has to be a member of any core coalition. And now we can see that there isn't any weak blocking to that. Now, what about the red allocation over here, for instance? So that allocation could be weakly blocked by agent 2, who actually could just go with agent 3. So here 1 and 2 are together, and that gives agent 1 the best thing. But agent 2 could also now block in a weak blocking with agent 3 and move over here, and agent 3 is better off. So basically, between the green and the red partition, agent 2 can flip back and forth, and basically these are core allocations, but not strict core allocations. So the strict core is just the grand coalition, and the core contains these other 2 allocations, so we can have a subset. So, sorry, this is too fast. So now the point is, how do you find core allocations? And now it turns out there's this really neat thing going on, that you can construct a nice graph, and the graph theoretical concept gives you a core allocation. So what type of graph is it? It's a very simple graph. Everybody is a node in the graph, and what you do is you point. It's a directed graph. You point at your friends. So here agent 1 has only friend 2, but agent 2 is a bit more social. He has friend 1, 5, 8, and 3. So everybody points at their friends, and you get the so-called friendship graph. And now it turns out that strongly connected components of the directed graph are important. So what does it mean for a set of nodes or vertices in the graph to be connected? it's a directed graph. So suppose I have a vertex here and a vertex here. I have to be able to walk on a directed path from vertex A to vertex B and from B to A. So in other words, a set of nodes is connected if any two nodes are on a directed cycle. Now, why do we say strongly connected components? Well, a strongly connected component is a set of nodes such that when you increase the set of nodes, it's not connected anymore. It's a maximal connected set. So here in the graph, I of course already marked them. This is a strongly connected component. This is one. So the dotted blue area, the nodes that are encircled by the blue cycles are actually strongly connected components. Now, those are sets of agents. So hence, a decomposition of a graph into strongly connected components induces a partition of agents. Now let me mention that strongly connected components can be computed very easily. There are polynomial time algorithms, for instance, one by Tarjan. Also, the decomposition is unique. There's only one. So I get a unique partition out of this. So we call this the SCC, the strongly connected components partition. Beautiful. So we have the first main result of the paper that for each problem with friend-oriented preferences, the SCC partition is a strict core partition. So it's not just a core partition, it's in the strict core, meaning the strict core is non-empty. Okay. Now the strict core does not need to be a singleton. We don't have that. Here's an example. It's again similar to this, but now agent 2 prefers friend 1. So this here is a better friend than the friend 3. So now your preferences look like this. And now what you can see is that the grand coalition, again, is a strict core allocation, but so is coalition 1, 2, and 3 is alone. Because again, here you don't have a weak blocking because, so basically for this one, for agent 2, to get better off, he needs the grand coalition, and that's worse for agent 2. So now basically you can verify that there are two strict core allocations. It's not a unique concept. But if you observe something here, you see that the second strict core partition is a refinement of the SCC partition. So it's taking the SCC partition and just splitting it in smaller pieces. And that is actually a structural result. It's a necessary condition that if a partition is core stable, not just strict core stable, then it has to be a refinement of the SCC partition. So we know a little bit about that. Okay. There's a corollary, and this plays a role for the next set of results or mechanisms, namely that if you have a component that is a simple cycle.
10 minutes.
I have 10 minutes. Okay, thanks. If you have a component that's a simple cycle, that component occurs in each core stable partition. I'm skipping this part, it's not so important, but this result is important for what comes next. Next, we look at mechanisms that solve problems whenever they occur. A mechanism is a function that takes subdomains from the friend-oriented preference domain and assigns a partition to each problem that occurs in that subdomain. Just notation, not so important. A mechanism satisfies strict core stability, individual rationality, Pareto optimality, if and only if it assigns these partitions with these properties. Strategy-proofness means that it's a weakly dominant strategy to tell the truth. So if one agent changes his report independently of what other people do, he cannot be better off. We also look at group strategy-proofness. If a group of agents, you don't need to look at the formulas, group of us splits off, reports something else, it should not be the case that we are all weakly better off and some of us are strictly better off. I will later introduce weak group strategy-proofness, which uses the strict manipulation. We get together, we report something else, and everybody is strictly better off. So that will be called the weak group strategy-proofness. The mechanism that always assigns the SCC partition is called the SCC mechanism. And the mechanism that assigns the SEC partition is strictly core stable, we know that, but it's also group strategy proof. I'm not going to talk much about the proof, but the point is there's something really nice happening. You know that if you have a decomposition into SCC components, you can define the so-called condensation graph where each component is shrunk. You just contract this into a single node, and whenever it has an outgoing arrow, that remains an arrow in your graph. So you can obtain a condensation graph. That graph is acyclic, and the acyclicity is important to prove things because inductively you start with the sink nodes of the condensation graph. You can show things for those guys because those guys consider everybody outside enemies. And that helps to show that actually they don't have an incentive to manipulate their preferences. So you can show this group strategy proofness stuff using the condensation graph structure. Now, is this the only mechanism that satisfies these nice properties, right? And in fact, we need some domain richness condition here, which is very natural. A domain from the friend-oriented preferences is rich if for each possible set of people you can be with, there is a preference report where you can declare those your friends. I'm able to make any of you my friends. So any set of you, I can make my friends in the preference domain. So then I have a rich domain. And then a mechanism on a rich domain is core stable. So now notice we are talking here about strict core stability. Where is that? Oh, that was before. We were saying the SEC mechanism is strictly core stable and group strategy proof. But now I'm weakening this to core stability and strategy proofness. And I'm claiming a mechanism is on a rich domain is core stable and strategy proof if and only if it's the SEC mechanism. So to pin down the mechanism, the weaker properties are enough. But it satisfies the stronger properties as well. Okay. Now we constructed some mechanisms that show independence. I had individual rationality and Pareto optimality up there because one of the it's not possible to weaken stability into Pareto efficiency and individual rationality because then we have a mechanism that satisfies that and strategy proofness. Now this is the main result, right? So I have 5 minutes, but I still want to tell you that we did think about what happens if you drop the lexicographic aspect. For instance, if you make it more important that you minimize the number of enemies. Now, then results don't hold because then already you lose the existence of core partitions. The core may be empty. So you have no hope to get even further results because now core stability doesn't have a lot of bite. On the other hand, what we could do is we can add neutrals. Now adding neutrals, this is the friend-orientedness conditions. The only thing you add is that you say, listen, when you add a neutral, your set remains indifferent to you. So they're truly neutral. Now then, we have a notation and stuff. What is this example about? This example now shows that the strict core can be empty because you have lots of indifferences. I'm not spending much time here. But actually, the SCC partition is still a core allocation. So the core is non-empty. Strict core can be empty. Does this thing satisfy group strategy proofness? The answer is no, because again, this example serves basically agent 2 can make agent 1 or agent 3 happy by just declaring them their friend, and he doesn't care. So it's not group strategy proof. However, weak group strategy proofness is going to be satisfied. Here we have an impossibility theorem to have actually core stability and group strategy proofness. I'm not spending much time here. I just wanted to say that we still can preserve weak group strategy proofness because when we have friend-oriented preferences with neutrals, I already explained this to you, it's a strict benefiting notion. So then the SEC mechanism is core stable and weakly group strategy proof, but there are actually other mechanisms that satisfy it now. because now you can merge in different sets in a certain way, and it gets quite complicated. With this, I would like to thank you and all speakers of the session. And
10 minutes for questions. Actually, may I ask one?
yes, please.
The rich domain part, usually one needs to put restrictions to get some existence result. Looks like you are.
So for the existence, we are fine, right?
What's the intuition for keeping the domain rich?
So I mentioned to you that when we have a simple cycle, then basically that always has to be a component. So the proof of the characterization result essentially starts with one observation, that if you start deleting friends from a profile such that the SEC components don't change, then the solution outcome has to still be the same. Yeah, so basically you can assume that your graph is minimal with respect to the components. Observation 1, then we start with a proof that says, well, if one of your components is a cycle, we already have the result that that component has to occur. Now what we do is in a double induction on number of vertices and nodes, so this is super fun. The next step is basically when you now have I just put the pen back. So this case is clear. So now you essentially solve this case by twisting it back to that. And when you understand this, you understand that that's the induction step where we reduce on the number of edges, because this has one more edge than this one. So when you manage to go back, you understand that there's a little trick you can be doing in your induction. And in order to be able to go from here to here, you have to be able to declare different friend sets. That's the intuition. Anybody else? If not, yes?
So because of the blocking, this is all like very computable, like in polynomially, or even better than that, right? You're not having any problems of like situations where this is non-polynomial or
no, absolutely not, because the point is the strategy-proofness forces the mechanism to just look at who are your friends. Basically, what this says on top, I didn't mention it, but it's a good question. It says, listen, forget about your whole preference list. Just tell me who your friends are. Right? I don't care if Attila is my best friend and you are my second best friend. It's just they are my friends. We don't care about that information. So the strategy-proofness forces you to ignore a huge part of your preferences. And that will be fine. And then the computation of the SEC components is polynomial. These are old algorithms in graph theory. They work wonderfully well. It's a bit like you talk about single peak preferences for certain things, for voting or whatnot, and you say, forget about the whole preference relation, just give me your peak. That's what strategy-proofness does here. Thank you. We can discuss all our papers in the coffee break now. Thank you.